All right, welcome to lesson 1.6 on continuity. It's the last lesson in chapter 1. So we've kind of hinted around continuity when we've been taking limits, but today we're going to actually define it in terms of limits. So a function y equals f at x is said to be continuous at a point x equals a if the limit of f at x as x approaches a is actually equal to the y value when you sub in x is equal to a. And we talked about this in that true and false about the flowing through the point. And that is our definition of continuity. The limit should be the same as the y value. Otherwise, we say that f at x is continuous at x equals a. So visually, again, we're flowing through the point. So the limit from both the left and the right is approaching this height f at a, but there is actually a filled-in point at that point. And again, the flowing through, tracing through it without lifting your pencil. So different types of discontinuities that we can see. There's three main types. There's removable discontinuity, jump discontinuity, and infinite discontinuity. So a removable discontinuity, your textbook refers to this as a point discontinuity, but throughout my education, I heard removable more often. The same thing. What we've got here is a hole in our graph. So I'm tracing along my graph, and all of a sudden there's this tiny little hole in the graph, and then I continue on. Remember, when you're looking on Desmos, you don't even see the hole unless you actually take your cursor and drag it along the curve, and then it'll tell you it's undefined here. In this particular example, the hole is just a transferred point down here, but that point doesn't have to exist. It would still be called a removable discontinuity without this filled-in point down here. A jump discontinuity is when the limit from the left does not equal the limit from the right. And here, the point f at a could be filled in on one of these ends, or it could be in a third location. So here, again, I'm flowing along, and then I have to pick up my pencil and jump vertically for this one. For this one here, I was just jumping over the hole and continuing. Notice that the limit from the left and the right were actually approaching the same value, but here I'm approaching two different values from the left and the right. An infinite discontinuity is when I'm approaching infinity or negative infinity on one side of the a value. So here they're showing I'm just approaching infinity on the right side of the point, but we've seen with rational functions that I could have like this here would be an infinite discontinuity at x equals 0. I can also have my pen is so thick. Okay, I could also have a infinite discontinuity. We saw some of these graphs in advanced functions where the two sections are both on the same side of the axis like this, and here they're both approaching positive infinity. And again, this would be an infinite discontinuity, right? There is still a discontinuity between these two sections, and I would say the discontinuity at a. When we write the limit as x approaches a of f at x equals positive or negative infinity, then what we're technically saying is the limit doesn't exist. There is no limiting value here as I approach a from the right-hand side. It's going on and on forever. But we can write infinity just to kind of give an idea of our understanding of the situation, even though infinity is obviously not a limiting value. So technically, this limit does not exist. All right, we're going to use the definition here to determine discontinuity. Sorry, I'm just checking my notes, making sure I said everything else. Up here, limit, the removable discontinuity, this is like the limit exists, right, here, but it just doesn't equal the y value. Just another way to say the same thing that we've got right here. Here, the limit doesn't exist at all because the left-hand limit does not equal the right-hand limit. Oops. Sometimes you'll see this short form DNE for does not exist. And then here, we're going to see infinity on one side or both. All right, so using that definition to determine continuity. Well, this one here, the first example is a quintic function. So it's just a polynomial function. So I'm going to write down my understanding. Okay, so I know then by limit properties, remember we talked about that, the very first limit property was about polynomial functions. And it told me that the limit as x approaches a of f at x is going to be equal to f at a for all values of a belonging to the set of real numbers. This symbol here means for all. You can just write the words. So because this is true by that limit property, I know then that this f at x is continuous for all values. And so it's asking for the intervals of continuity. So I'm going to put this in interval notation. So f at x is continuous everywhere. All right, our next function here is a rational function. And the first thing I'm going to do here is factor the denominator. So I've got a difference of squares. All right, so I know then that g at 4 and g at -4 do not exist. So that tells me then the limit as x approaches 4 of g at x can't be equal to g at 4 because it doesn't exist, right? So they can't be equal to each other. And also the same thing for -4. It can't equal something that doesn't exist. So then by the definition, this is the definition, right, of discontinuity. These things have to be equal for continuity. So therefore, there are discontinuities. So notice here that I'm using a calculus argument. I'm not using my knowledge of rational function patterns from advanced functions, which really, we didn't talk about why it always works or why it's a discontinuity. Now we're actually coming up with like a mathematical definition. I'm not just saying like, oh, the patterns show this. And this question did ask me to state the intervals of continuity, so now I need to say so there's actually 3 intervals of continuity, starting on the left up to -4, then from -4 to 4, all round brackets because I don't have continuity at -4, so round brackets, and then 4 to infinity. Remember that in interval notation, we use a square bracket to indicate if we're including the value. All right, next example here, we've got a piecewise function. So when I've got a piecewise function, I can say that I know that h at x is continuous for x less than 5 because it's a polynomial when x is less than 5. And then same thing for when x is greater than 5. I know that it's a polynomial. What I want to know is, does this line run into this line at x equals 5, or is it like a jump discontinuity? So what I want to figure out first is what is the value of the function at that point of interest. So if I'm plugging in x is 5, then I'm looking at this function, right? Because this one actually has greater than or equal to 5. So I'm going to do 2 times 5, 2 times x. So I've got my y value. Now I need to take a look at the limit from both sides, and I need to make sure that the left-hand limit equals the right-hand limit equals the y value in order to have continuity. So first I'm going to come in from the right-hand side. So I'm looking at this one again. Oops. And here I can start doing direct substitution right away. And what do you know, I got the same y value. So now we're going to check the left-hand side. Now if I'm on the left-hand side of 5, then I'm in this domain, and so I'm going to use this equation. Don't forget here, as soon as I've got that addition or subtraction, I need brackets here to say I'm taking limit of the whole thing. And then I'm going to plug in x is 5 because, again, direct substitution will work here. and I get 9, which is a sad face. This is not a continuous point here, right? So therefore, the limit as x approaches 5 of h at x does not exist. And so therefore, h at x is discontinuous. At x equals 5. And therefore, I can list the intervals of continuity. So I might not give both of these last two statements depending on what the question is asking me for. So they technically in this question don't ask me, let me just double check here. They don't ask me to state the discontinuity. So I don't need this second last sentence, but I do need this last one here. So just make sure you're reading the instructions of the question. Okay. Our last example is a radical function. So we might want to think about what this function looks like. And thinking about our knowledge of limits, right? I know that I can take the limit, taking the limit of the root is the same as taking the root of the limit. And I know then that I can take the limit of any of these, of this polynomial that's under here. But what is interesting about this function is I've got my root function. It's been shifted over to +1 on the x-axis, and then it's been reflected and horizontally compressed. So it opens to the left instead of opening to the right, and it's been like horizontally squished in. So this is kind of what it looks like. So what I'm suspicious about then is what's going on at x equals 1. That's a suspicious value for me. I can see here that all of these guys are continuous. So I'm going to check out x equals 1 because he's suspicious. So first I'm going to find the y value. And so you can plug it in here. And we get a y value of 0. And then we're going to take a look at, well, what's the limit as x approaches 1 from the left and the right? So as I approach the limit from the left, so I'm coming in from this side, that's okay. I can take the limit of this, and using my my limit properties, I know I can just substitute this in. And so I get 0 as above. Then I'm going to approach from the right. So now I'm thinking about approaching from like 1.001 or something like that. And if you think about plugging 1.01 in here, then, or sorry, yeah, 1.01, then you're going to get like 0.001 or something like that. And then you're going to multiply by -3. And that's a negative number altogether, right? Because this bracket turns out to be positive, and then you multiply it by this negative. And you can't take the square root of a negative. So this limit does not exist. And so therefore, the limit as x approaches 1 of k at x does not exist. And in order to have continuity, the limit has to exist. And so here, k at x is actually continuous for the whole domain of this particular function, except for at the point 1. So I put a round bracket on that point. All right, for our next example, this time we're given the continuity of the function, and we actually have to figure out some of these missing values in the equation. So we're missing this coefficient here, and I'm missing this constant here for this piece of the function. Now in this question, I've been told that it's continuous everywhere. So I'm continuous for the whole thing. I also could have said that it's continuous, from -∞ to -2, and then from 2 to infinity, in which case this would be continuous, but this would not be continuous at -2. So they could give you different scenarios. we're going to take a look at it's continuous everywhere. So when I look at these three pieces of the function, each of these pieces is a polynomial, so I know that there's continuity within each piece. What I want to know is there continuity between each piece? So I need to take a look at -2 and +2 and figure out if they are equal to each other. So I'm going to be looking at the limiting value from both sides of -2 and the limiting value from both sides of +2. So first, taking a look at -2, so I'm approaching -2 from the left for f at x, and when I do that, I need to figure out, well, which piece of the equation is that? So I'm looking at -2 from the left, that's this domain, so I'm looking at x plus 3. And for this one here, I can use direct substitution, so I'm going to just plug in my x value of -2 and take the limit, and I get the limit of 1. And then I've got the limit as x approaches -2 from the right, from the positive side. So I'm going to go and figure out, well, which part of the equation am I using? So if I'm approaching -2 but from slightly bigger than -2, I'm in this domain here. So I'm going to use this function, this parabola. Oh, and I made a mistake up in the first part. Hopefully you saw. I forgot my brackets here. I need brackets here as well. All right, so now again, I've got a polynomial, so I can use direct substitution. Don't forget, when you substitute in a negative, the brackets are necessary. I am squaring the negative, so it turns into +4. Okay, so we've got an expression here in terms of a, but that's one of our jobs, right, is to figure out, well, what is the number for a. So for continuity, at x equals -2, we need the limit to exist. So we need the limit from the left to equal the limit from the right. So that tells me that I need 1 to equal 4a plus 5, and then I can solve here for a. So bringing the 5 over and subtracting, and then dividing out the 4. All right, so I know then the a value is -1. You can substitute that in at this point, or I can bring it back in later. We figured out the continuity at -2. Now we need to figure out the continuity at 2. So we're going to do the same process, but looking at the limit as x approaches 2 from the left. And so if I'm approaching 2 from the left, I want to be slightly smaller than 2. And so that tells me I'm using this parabola. So again, you could put the 1 in there at this point. I'm going to put it in later. So again, I can substitute in the 2 because it's a polynomial function. And I get 4a plus 5. Now we're going to take a look at the limit as x approaches 2 from the right. If I'm approaching 2 from the right, I want to be slightly bigger than 2. So I'm looking at this domain here, which tells me to use this equation, x plus b. All right, we've got a polynomial function, so I can use direct substitution. And I've got my expression. I'm just going to rearrange it. All right, so for continuity, we need the left-hand limit to equal the right-hand limit. So we need 4a plus 5 to equal b plus 2. So at this point, I'm going to sub in my a value. And I get -4 plus 5. And then I can solve for b. And it's actually the same as a, -1. So I still need to write my summary sentence, but before I do that, I just want to talk about, well, what if I wanted discontinuity at one of these points? So let's say I wanted discontinuity at x equals 2. Well, then what I would be saying So I'm just going to change that question. Say I wanted discontinuity at that point. Then I would want these things to not be equal all the way down. And so b could be any number other than -1. So I could pick any other number for b and I'd be fine. Like I could pick -1.07 and that would work. Or 105. It doesn't matter as long as it's not -1 if I wanted discontinuity. All right, my summary sentence for this one. So the question asks you to state the values. I'm going to restate the whole function. I'm just plugging in my a value and my b value and then restating those domains. So if I have this function, then I know that it's continuous on the whole domain of the set of real numbers. All right, that's it for today's lesson. You can find the homework on the homework log. Enjoy!